Thank you very much for coming to this well, not very early, but those of you who were at the YSS event last night, slightly early, YSS and Research Section event. This is the event for the first annual RSS Statistical Analytics Challenge. This challenge is run in collaboration with Select Statistics, who sponsor us, and it's a collaborative effort between the Research Section in the Royal Statistical Society and those of us in the YSS. So just to give you a brief outline of how exactly the challenge worked, the challenge was run over 6 weeks over the summer. We had 18 teams who registered from around the world, and the teams were given access to an online brief for an analysis that they had to do. So the analysis was based on fMRI data, and the idea was looking at the perils of data dredging. The teams had complete freedom over what sort of analysis they wanted to do, and what we were looking for were innovative types of analyses and different ways of looking at the data set. There was a minimum data set that the teams had to work with, but apart from that, they had free rein to do what they wanted to do. So about halfway through, all of the teams, if they wanted to, could receive feedback on their work plan, and that was given by our team of judges from the research section. And after that, then in the end of week 6, the teams submitted a full report. Those full reports were then judged by our team of judges from the research section, and 2 winners were chosen. The prizes there were 3 main prizes. The first was this session, so all of our teams who are over in this section over here gathered together. They are here as invited speakers for the Royal Statistical Society Conference. And then the other prizes were written feedback from the team of judges, which will be given to you guys after this event, and then also any report that was deemed to be of significant standard would be submitted to the Series C journal. So just to give you an outline of how today's event is going to run, first of all, we'll have the prize giving. So we'll have prizes from the chair of the research section, Chris Jensen. He'll say a few words about the research section, and then we'll give the prizes to the 2 teams. Then our overall winners will present their paper, and then that'll be followed by the highly commended runners-up. After that, John Aston, who was one of our judges and who helped to set the challenge, will be discussing the challenge overall, and then we'll open it up to the floor. Okay, so without further ado, Chris Jensen from the RSS, our research section.
Good morning. It's a real pleasure for the research section to be associated with this challenge. I'd just like to take a little bit of time to explain something about the research section, because I'm not sure that sort of all young statisticians are familiar with exactly what we do. The discussion papers, the red papers that you see in the journals, are, at least some of those, are the product of meetings of the research section, which consider submissions of papers for reading. If you haven't ever been to one of the meetings where the papers are read, you really should. They're great events. Most of the discussion that appears in the paper was actually discussion at the meeting. Some comes later in writing. And I'm sure you've come across in your research papers that you've gone back to in the journals and seen all the comments, some of them saying what a great paper this was, some of them explaining why it's all wrong. And there are some real landmark papers in that area. The Cox's 1972 paper had its own 40th anniversary celebration a couple of years ago. But there are many more. So it's something to aspire to have work gain another level of publicity and respect. So I would encourage you to follow that route. But for today's event, we're looking at the challenge, and congratulations to all those who took part, but our winners and honorable mentions in particular. And I think it's now time to give your awards. So can I invite up Team Soda? And Team Soda come from the University of Nottingham. And we have listed Chris Brignall, Philip Payne, Wilhelm Brown, and Heather Pettit. And our overall winners are Team UCL Stats, which comprised Beata Frank, Sam Livingston, Alfredo Kalaitsis, and also Michael Betancourt, who's at Warwick University.
Great, so congratulations to both of the teams. So Team SODA and Team UCL Stats will now present from the reports that they submitted for the RSS challenge. And first we'll have from UCL Stats, who were the overall winner, Beate Frank.
Hi everyone. My name is Beate Franke. As team leader, I have the honor to present our group's contribution to the RSS challenge today. Our group, as you've already seen on the stage, is Sam Livingston, Michael Betancourt, and Alfredo Kalaitzis. We would like to thank very warmly Ioana Manopoulou for all her support. Ole was so kind to give a rough introduction to the RSS challenge itself, so that our presentation today will start with giving you an idea about the dataset. So we were working on the 1,000 connectome dataset, which, by the way, is freely available. This dataset includes resting state functional MRI images of human brains. So whenever you have functional MRI images, what you have is you've got a 3D image of the brain, and you've got a time series of this image, okay? Every single of these images gives you intensities for different locations within the brain. I'm not going to tell you what these intensities actually measure, because for today's talk, the only thing you need to understand is that these intensities let us conclude how active this part of the brain is at the given time point. In the past, what has been done the most is you have a patient and you put him into the MRI scanner and you expose him over time to different stimuli. A stimuli could be any image, anything which is triggering activity within the brain. And then you have a look how the activity within the brain is changing over time due to these stimuli. In the recent years, neuroscientists have realized that even if the brain is at resting state, so no stimuli whatsoever, there are still regions within the brain that are active. So our dataset, the dataset we worked on, is resting state functional MRI images of human brains, okay? From all the questions the neuroscientists would be interested in, we've chosen to analyze distant regions within the brain that are functionally connected. Let me say this with other words. So for each of these locations within the brain, we've got a time series of its activity. And we are interested to find spatial temporal correlation within these datasets. Functional MRI data tends to have two characteristics. First of all, it is very rich in the sense that it's very high in resolution. What do I mean by very high? For a single patient, we have tens of millions of data points. I think all of us are going to agree an exhaustive analysis of this dataset would be computationally intractable. And the second one is that you have, on top of the signal, you have noise, as always. But this noise is high in frequency, and it's not just white noise, it is structural noise. This is making the problem a little bit more challenging. But there's a common practice how to solve this kind of problem. Let me talk you through the common practice. What you see here is a 2D slice of a brain. We have worked on 3D images, but to give you an idea, this will do. These brain images are discretized into these locations within the brain, which from now onwards we're going to call voxels, just following the literature. So what people do is, the general strategy which people use to analyze this kind of data set is a two-step strategy. Within the first step, they reduce the data set so that in the second step, they actually can apply algorithms to infer spatial temporal correlation, okay? There's a theory behind why this data reduction step actually makes sense. The neuroscientists agree that if you have a look at voxels that are active together, they are generally speaking not scattered all over the brain, but instead they tend to gather within local regions. So what people try to do in the first step of the data reduction, they try to identify these local regions of interest where the voxels within these regions are similar, so that then they can do the second step and apply algorithms to infer spatial temporal correlation. How do they do that? To find these regions, you need to take a pair of voxels, and you need to decide if this pair of these two voxels are actually similar. If you decide based on their time series that they are similar, what you do, you draw an edge. If you do this with all possible pairs, what you get is a network. So now you can fall back on the literature of network science, where lots of things have been published about clustering, and you can pick one of these clustering algorithms and you can cluster your data. So what you now have is you've got your voxels, you've assigned them to clusters, and hopefully, depending on how good your similarity measure was, you actually have regions of interest where the voxels within each region are similar. This is the first step. If you then gather the whole data so the whole time series of one region of interest, and you can kind of summarize it to one time series, you've reduced your data set massively, which gives you the opportunity to actually apply in the second step algorithms to analyze this data. We followed the same general strategy, and I'm going to talk you through this two-step strategy, and I will flag what we did differently, okay? So first, let's start with the data reduction. For today's presentation, I will focus on two main questions. The first one is, does it actually make sense to define these clusters? And the second one we want to go into is how to actually choose a reasonable similarity measure, because all the analysis will be based on how well our similarity measure works. What you see here is a plot we've chosen, by chance we've chosen some voxels, and I'm plotting here the time series of their activity. So each of these lines belongs to a single voxel, and you see like its activity over time. The idea is that the way we want to define our clusters, they are static in time. So if we now have the brain and we have defined clusters within the brain, if now we have a clear trend within the intensities changing over time, we would expect that defining the cluster static will not work. The clusters would need to change with the trend, kind of. Okay? So the question at hand is, are these time series actually stationary? And we run some tests, and we could conclude that, yeah, the data is second-order stationary, which allows us to define our cluster static in time. So far, so good. The next step will be to find a similarity measure that let us allow to judge reasonably if two intensities of voxels are actually similar. And what has been done in the past is to use the Pearson correlation. As all of us know, if you have the Pearson correlation, or any linear correlation, will be very sensitive to fatter tails than for a Gaussian distribution. So what we did, we checked if our voxel intensities are actually Gaussian distributed. What you see on this slide is one example of a QQ plot of the intensities of a single voxel over time. And as we've seen for lots of other QQ plots, what you can see is that the lower tail does not agree with the normal distribution. This brought us to the conclusion that we do not want to assume normality, and instead we've chosen our similarity measure to be non-parametric. Okay, for the non-parametric similarity measure, what we decided to choose is a Kullback-Leibler divergence between the joint empirical distribution of two voxel intensities, and we want to take the Kullback-Leibler divergence of this one compared to the product of the two marginal empirical distributions of the voxels, okay? What this basically does is it compares the observed joint distribution with what we would expect if those two voxels would be independent. In addition, we do estimate our distributions by histograms to keep it non-parametric, so that we do not need to make any assumptions on the distribution of the voxel intensities. What you see here on the slides, on the slide is, Shaul emphasized the point a little bit better, what the Kullback-Leibler divergence actually does. So on the down part and on the right-hand side, you see two marginal distributions. This is simulated data. And in the square in the middle, you see they are joint distribution, but these two marginals are strongly dependent. The similarity measure we've chosen will compare the square in the middle to how it would look like if you would just multiply the down part and the right-hand side. So for instance, this part here would be, if you would just multiply it, should be way more yellow because you have very low values here, and so on and so forth, just to give you an idea. So we have a non-parametric similarity measure. What we will do with it is, as described before, we have our edges. We define the edges based on the similarity measure. We do some slightly divergent version of an algorithm for clustering, and we get these regions of interest. We've decided to go for 100 regions of interest based on the literature. You see here only 30 to make it a little bit more visually appealing. And if you look at this for long enough, what you see is that our regions of interest have some kind of symmetric structure across the YZ axis. The YZ plane for x equal to 30, like here, you see that along there, there's a symmetry. There's a symmetry along there, and this symmetry is actually agreeing with the symmetry between the left and the right hemisphere. Why this is so interesting is that we did not put in any of these as assumption, but instead it's just going to be, it's just going to come out of the approach we used to analyze the data. So far, so good. But this is not actually the interesting part. The interesting part is, does our regions of interest keep the signal? So let us have a look at the signal. Each of these lines is giving you the intensity over time of a region of interest. We computed these intensities by taking a weighted average over the intensities of the voxels within one region of interest. And the nice thing you can see here is that the signal is actually preserved. So we started off with tens of millions of data points. We reduced it to tens of thousands of data points. So we took a weighted average over lots of voxels, but the signal stays. Let me sum this up. This was the first step of our strategy. It was the data reduction step. So we started off with tens of millions, and we ended up with tens of thousands of data points, which is a very nice reduction. We used a robust similarity measure, and due to that, we were able to preserve the signal. This brings us to the second part of our strategy. We now want to have a look at a higher level, and we want to infer the spatial temporal correlation between these regions of interest. Since we have averaged over so many of these time series, it's not too surprising that the time series of the regions of interest are approximately Gaussian distributed. This is just the classic central limit theorem kicking in. This allows us to model our data as a Gaussian Markov random field. And there has been done a lot of work on this, which is telling us that if we look at the precision metrics, for those of you who haven't come across the precision metrics, it's just the inverse of the covariance metrics. If we look at the precision metrics, we are able to factorize it into the temporal precision metrics and the spatial precision metrics using the Kronecker product. Doing this allows for fully connectivity across space and time. This sounds all quite theoretical. Let me give you a better intuition about it. What we want to have fully connectivity across space and time. So we start off with having spatial precision metrics. This is S. S is reflecting the network within space, so the human brain. Then we have a temporal precision metrics, which is related to how we allow our regions of interest actually connect across time. And then we take the chronic product of these two, and what we get is the precision matrix on the right-hand side, the network on the right-hand side, which is very densely connected. And as you can immediately see is, even if you have just very small networks, this is going to get very complicated very soon, and it's not going to be tractable. In addition, if you do inference on these, in this situation, you have to solve a non-convex problem. So we decided to step away from the fully connectivity across space-time. Let me give you a quick hint here. When we say fully connectivity across space-time, what we mean is we have the human brain, we have the regions of interest within this brain, and we want that every regions within space are allowed to be connected. In addition, we want that each region of interest is able to be connected to every other region of interest across time, so that we have fully connectivity within this huge network where we connect the human brains across time within one network. So this is not going to be tractable. So what we did, we fall back on some work Alfredo did within the past year with some of his colleagues, which is saying, okay, we want to keep the fully connectivity across space. So we want all voxels within one brain to be allowed to be dependent on each other. We want to keep that each region of interest is connected to itself in any other time point. So we want to keep fully connectivity across time, but we want to restrict connectivity across space-time. So that if I take one region of interest within one brain, we want not to allow this region of interest to be connected to another region of interest at another time point. Okay? If we can agree on this assumption, what this gives us, based on Alfredo's work, is that now we can factorize the precision matrix into the chronic sum of the spatial and the temporal precision matrix. This, in turn, is equivalent to solving a convex problem, which is very nice. Alfredo did not only did they derive the theory for this, what they did in addition, they implemented it and they published an algorithm which infers the parameters within the spatial and temporal precision matrix simultaneously, and it's computationally efficient. Let me show you some results. So we have, these are the results for the temporal precision matrix. Let me mention that we took off the diagonal, so we set the values of the diagonal to 0 to add visibility. And let me also mention that since we talk about precision, very red values, so very negative values, indicate a positive correlation, whereas blue values, so very positive values, indicate an anti-correlation. So what I would like you to see is that on the diagonal, there's a tendency to have lots of red values, whereas on the off-diagonal, we have a tendency to have blue values. This is telling us that if you take regions of interest that are close in time, they tend to be correlated, whereas if you take the same regions of interest, which is further apart in time, it's anti-correlated. It tends to be anti-correlated. Let's talk about this, our results for space, for the spatial precision matrix. The index here is the cluster index. So there's no way you can relate this back to the spatial image of a brain. The only thing I want you to take out from this image is that we actually found really red and really blue values. So we actually could show that there is real correlation and real anti-correlation between these regions of interest. To give you a better intuition about the spatial connectivity, what we did is we plotted this back in time, back into space, putting an edge between two voxels that are strongly correlated or strongly anti-correlated. So we now only take into account dark blue and dark red values. And that leaves us with these results. And what you can see here is that we actually identified regions of interest that are correlated. And if you look at it for long enough, what you can see is that we recovered the symmetry and the shape of the brain anatomy. One second, technical problems. Let me sum this up. we found distant regions within the brain that are functionally similar. We did so by reducing the dimensionality in a novel way, which gave us the opportunity to apply state-of-the-art algorithms to infer spatial temporal correlation. Thank you very much for your attention.
So our next presentation will be from Philip Payne and Heather Petit from Team SODA, our highly commended runners.
Thank you for your time this morning, and special thanks to the organizers for setting up this competition, because we all had a lot of fun learning a new field, which I think was the motivation for us getting involved. And hopefully you continue to run it in the future, and anyone who is thinking of taking part next year, if you have one, then you definitely should get involved. It was a lot of fun for us. So we are Team SODA, which is the Shape and Object Data Analysis research group at the University of Nottingham, and we will present our findings from our investigation. So I will discuss the challenge briefly, because it was already discussed by the previous speaker, and discuss some exploratory investigations that we had to make. And then Heather will talk through the research question we focused on, the workflow or the methodology of our approach, and then discuss the results and conclusions. So we already heard from the previous speaker what the challenge was about, which is that we were just given some fMRI data and told to investigate some statistical analysis, and with the important focus being on highlighting the potential pitfalls for researchers in the field. And that was one of the rules when we had to use this data set, so we focused on this one in particular. So if you're not familiar with these techniques, this is in a very basic form what happens. In MRI, you're looking at excited hydrogen atoms, and particularly the rate at which they return to equilibrium lets you determine between which type of tissue you're looking at, which allows you to build up the images. And fMRI is that applied to blood flow. So specifically, you're looking at the oxygenated hemoglobin in the blood in the brain, and that will tell you which parts of the brain are active during usually you're presented with some external stimuli, so it's how your brain reacts to seeing certain images. But in our case, we were given resting state data, so there was no external stimuli. You're just sitting there, but the brain is never fully off. There is still activity occurring, and that is what's being recorded in the fMRI data. And the aim of the project is to discover what areas of the brain are interacting. And there has been a lot of previous work done in this area, particularly by looking at demographics such as age, gender, and particularly useful for some neurological disorders such as schizophrenia. And so the bottom there is some uses of this in the research field. So we were presented with this huge data set collected from 33 sites, and we chose to focus on just one of them. So this is just the background of the subject. The important point is that the data is 64 by 64 by 33, and that is for one image of the brain. So you're taking the brain 3D and cutting it up into small cubes called voxels, which then make up this image, and you're taking that over 225 time points. So you're taking an image of the brain, scanning it many times, and the TR 2 seconds refers to the interval between scans of the brain. Yeah. So the start of our exploratory investigation was to look at these pre-processing. This is an important step. Well, it is a necessary step when looking at data of this sort, resting fMRI data, because the data will contain a lot of noise and certain artifacts that you want to try and remove as much as possible before you begin any statistical analysis. Otherwise, it would. Otherwise, it will not be valid. The first two refer to physical effects. So the motion correction refers to a person's head is moving even slightly. When you're looking at the data, you want to be able to compare the same part of the brain over time. But if you're looking at your image and you're moving around, you won't be looking at the same part of the brain over the entire time series. The slice timing correction is the same idea, but that when you're taking your scan of the brain, you're taking it in slices through the brain. So that when you take the first slice and the last slice, there will be some time delay. So you must shift that the later slices back to so you're looking at each slice at the same time point. The brain extraction is related to registration, so I will leave that for a second. The spatial smoothing is also to try and remove noise from the data, and it does that in a way, it does that by looking at, we're taking a voxel, and then you consider neighboring voxels, and you average, or you smooth the intensity of that voxel by taking a weighted average of the neighboring voxels, and that way hopefully you remove artifacts, and you're just left with the true signal. Temporal filtering is the same idea. It's related to a trend that appears in the data that is from background noise and not from the signal. And again, you're trying to remove that with some smoothing to remove high frequency noise in this case. The last two, brain extraction and registration, are to do with if you're comparing particularly for multiple subjects, you want to make sure you're looking at the same parts of the brain in each person. So you map, in brain extraction, first of all, you're removing parts of the brain that you're not interested in. That is, you're removing bits of tissue and bone marrow from the skull image that you don't want. And then the registration step is to map each subject onto a standard brain space so that you always know that you're comparing like for like in terms of the voxels within the brain. And so if you use some the software in this area, this FSL, which is excellent software, and it comes with these default settings. So this is what for people who know the field, this is what we applied. But this will be the focus of our research question later. So for now, I will just present it, but we can ignore it for now. The statistical analysis, we are interested in finding out which parts of the brain are interacting during resting state. So the first step is independent component analysis, and the idea of this is a dimension reduction idea, again, so for removing noise from the data. So what one does, you can decompose the whole data, that is the image, the spatial map, the image of the brain, and the time series, and you can decompose all of that into a series of independent spatial maps and the associated time course. Yeah, so for one subject that is relatively straightforward, the problem is when we're looking at multiple subjects, you're then going to end up with independent components being a mix of these signals. And you need some way of getting back to the subject-specific components. And that is the idea of dual regression. So that is taking all of your independent components for all of these subjects and mapping them back onto subject-specific data sets so that the correlation, the network analysis is relevant. And so what we were looking at was to investigate the correlation between different regions of the brain to see if they are indeed acting at the same time, if there is some correlation between the structure. And then I will hand you over to Heather to discuss our research.
Thank you. So at this stage in our investigation, we have established broadly what each of these, the inbuilt functions in FSL does, what the purpose of all these pre-processing steps is, and which ones are necessary and which ones are perhaps optional, and also what are the options within those predefined functions. So also, being new to this field, what was it? So so we weren't really sure how to choose these pre-processing parameter options within the inbuilt functions. So we wanted to find out what happens if we do change some of these parameters. So how does our choice of these parameters affect final analysis? And we also noticed, we got the impression that this FSL package was perhaps initially set up for the functional fMRI, functional MRI investigation, so where you have a stimulus and you're looking for a response. So we wanted to check that even the default parameter settings, were they still applicable to resting state fMRI data? So we focused initially just on one subject, which was the one indicated in the challenge rules. So we applied 2 different pre-processing protocols to the same subject. So we just alter one of these pre-processing parameters. And then we perform the analysis and try to identify whether the results show that there are any differences in the analysis by changing the pre-processing parameters. And by choosing just one subject, we hope that this eliminates some of the subject effects. So the effect of age, gender, and centre. So we are solely looking at the effect of changing this one parameter value. So these are our default FSL parameters, the default functions that are used, and we are going to investigate the effect of the smoothing function, so the half width of the Gaussian filter that we apply to smooth the data. So we performed 4 investigations looking at a difference in 3 millimeters of this half width. And we also wanted to investigate the effect of no smoothing whatsoever, so 0 millimeters, versus the largest one that we investigated, 12 millimeters. So we performed the analysis, as Phil described, and we want to investigate whether there's any changes in the estimated network structure following these 2 different protocols. So if we were to see in these trends, if we were to see separation, so multiple trends within the plot, I'll explain what we're plotting actually. So along the x-axis we have the mean correlation structure of these dual regression components. So these are the correlations as estimated over the mean of the 2 different pre-processing protocols versus the correlations of the individual subject-specific components. So if we see a nice one clear trend like we do here, then that would indicate that we're not seeing any difference between the 2, the network structure under the 2 pre-processing protocols, which is nice. But here, when we're comparing no smoothing to 12 millimeter half width, we start to see some separation between the 2 groups. So it hints that there might be some differences between the correlations of these subject-specific components. We also observed that there were a different number of components required to explain the amount of variability required. So this is just an observation that we might investigate further. So in conclusion, we don't see any clear differences in the estimated network structure when we're just looking at differences of 3 millimeters in the half width. However, we see slight deviation when we're comparing no smoothing to 12 millimeters. We should note that our investigation is just looking at one subject. So we removed the effect of subject effects. However, in the future, we might choose to include
more subjects in that, so maybe different ages, genders, centres, just to verify that that had nothing to do with it as well. And of course, there are many other pre-processing parameters in these inbuilt FSL functions that we would also advise investigating as well. And some of our references. Thank you very much.
So now I'd like to invite John Aston to discuss both of the reports and the challenge in general. John was on our judging panel from the research section.
I was part of the judging panel from the research section committee that looked, and I was sort of primarily responsible for setting the challenge itself. Why did we set the challenge? Well, in some sense, we were actually really interested to see what people would do with huge sets of data that really, hopefully, most people wouldn't know a huge amount about. This is sort of counterintuitive, except it's what everybody actually really does. Everybody claims that they do analysis on data and they've got all this really, expert opinion they go and solicit, but in many cases, people analyze data and they look at it in such a way that they, do what they their classical statistical ideas and tests first and then hope that that means something. Well, what we wanted to do was, well, what happens if you do that in a formal way and you say, well, look, this is the aim of the exercise. The aim of the exercise is to say, what happens if you go and look at this data and you make naive choices? Do you get sensible results or not? And if you don't make naive choices, you actually really do the analysis carefully, do you get different results? So what we wanted to do is say, have you got new techniques or existing techniques? Could we get interesting information? And particularly highlight this idea of whether the statistics changes the kind of results in the subsequent analysis. And I think both teams we've seen have done a very good job of that. They've both looked at some naive methods and seen that in actual fact, if you just do the naive thing, you get different results than if you actually do some careful statistical analysis. So the challenge itself is based on fMRI data. Both teams have introduced fMRI to some extent, so I will talk about it a little bit just to give you a kind of idea about what you have. You have very large data sets, which are three-dimensional in space and one-dimensional in time, so 4D overall. They typically have something of the order of about 1 million data points. As both teams mentioned, these are comprised of voxels. Well, if you are happy looking at a two-dimensional picture and you have a picture element or a pixel, a voxel is a three-dimensional image with a volume element or a voxel. And basically, each voxel encodes a small little region of the brain, and associated with each one of those is some kind of time course. Now, this is a time course not from a resting state experiment, but from an experiment to do with a temperature, and a hot or cold stimulus was placed on someone's hand, and this is the kind of time series that you get out, where you can see that there was a change a fairly regular change in the stimulus, and this area happened to be associated with changing the brain's processing of temperature changes. So you have these kind of data, but what we had in the challenge was resting state data. Now, there were two reasons for using resting state data. Firstly, there was this very nice data set called the 1000 Connectome Project, which has about 1,200 subjects, huge amounts of data, not only fMRI data, but also anatomical data. So if you want to put the subjects together, there's anatomical data that allows you to look at the brain anatomy and see how different people's brain anatomy compare, and look to see whether there's either how to register people's brains together, so you can do multi-subject analysis, or even looking at whether variations in anatomy predict underlying functional results. But the other thing is that resting state data is actually quite controversial, because if you imagine putting someone inside an fMRI scanner and telling them to lie down at rest with your eyes closed, don't fall asleep, which is the sort of standard protocol for resting state fMRI, it's probably not the most restful environment in the world. MRI scanners, for those of you who've been in them, are kind of loud. And it's highly unlikely that this is going to naturally give you a stationary, very clean data set. So in some sense, what we wanted to see was what happens if you actually start at ground zero, start and say, I'm a little worried about the assumptions that are made when we do this. Is stationarity a valid assumption? Can we do the naive analysis on this kind of data where there really hasn't been any kind of formal experimental design? Someone's been shoved in a scanner, they've taken the picture of the brain over time, and then looked to see what the results come out. And we were interested in whether you can sort of, from a statistical point of view, validly analyze that. So we've seen two great presentations, and I think you'd have to agree that both our winners had really, really sort of sensible, thought-out methods for doing the statistical analysis. So starting with the UCL analysis, they used something which was akin to spectral clustering to remove the short-range dependencies by defining this nice distance metrics that allowed you to see how similar different voxels were and then to produce these regions. They then used graphical models, sort of this biglasso method, which was based on this kind of separable space-time covariance structure in order to define these nice sort of connections, which we saw in the nice revolving graph that between different brain regions. The nice thing about the biglasso algorithm was that it was computationally feasible because it had this separability built in. In actual fact, that's kind of a common underlying assumption that's made in almost all brain imaging analysis. People sort of pretend that they're doing these kind of full analyses, but separability is embedded in there almost everywhere because it's the only way to do things computationally. And they did some nice checks to see if things like stationarity was an issue. I very much liked in the report the idea of looking at the Pearson correlation and saying, look, this isn't sensible, because it's not. But they had an extra way of doing it, which was kind of nice. You sort of had a nice empirical, non-parametric way of trying to look to see how similar two things were. So I thought that was a very nice aspect to the analysis. We've seen these results already, but I just want to say why I think they're kind of nice. You get this really nice representation. Basically, what you say is the brain is a big system, and it has lots and lots of elements, but in actual fact, in most of these analyses, you can't really distinguish point by point different things going on at different places. A, it's not computationally possible, but B, you probably haven't got the resolution to look at it. If you're thinking about what an MRI scanner is looking at, each of those volume elements, each of those little boxes, on average, maybe 2 millimeters by 2 millimeters by 2 millimeters. If you think how many neurons are stuck within a 2 millimeter by 2 millimeter box, it's an awful lot. And so you've got all these neurons stuck in there that you're trying to either say are acting collectively as a system, or you want to say, well, in actual fact, probably if they're acting collectively as a system of a 2 millimeter block, you probably can make that assumption on a slightly bigger area. And this is what happens here. You effectively get these effective voxels, the particular regions here. These are the 30 regions out of the 100 that they showed that they performed in the analysis that represent differing spatial locations and different parts of the brain doing different things. And I like the way that they use this similarity measure to construct these to give you these nice representations that they then continued with their analysis. And you get the nice time courses out that you can then treat in a very sensible way. So it was a very nice way of doing the dimension reduction. So what would I say that they still need to kind of consider in their analysis? Well, I like the idea of producing the effective voxel, which I said was very nice. However, I would be kind of interested to see how that really relates to brain anatomy. If you've got the anatomical data there, can you kind of look to see whether these have anatomical relevance? I'm not worried if it doesn't, but if it did, it would be really interesting. Secondly, they had this idea of using very, very similar metrics. If it was 2 voxels away, then they kind of discounted it. Kind of, it's computationally probably necessary, but, can at least have an idea, maybe even with sort of small sample data, whether that makes a big effect on what they were doing. And then both teams mentioned this, and I'll comment on both, but the data came from this huge populational study, whereas both teams quite sensibly chose to focus on one individual subject. So how would you build in the population analysis? And I think for the ideas from UCL, there's 3 very interesting ways. You could either use the brain populations to define the effective voxels across a population, or you could take individuals' effective populations and use the population to build the kind of long-range dependencies for one set, or you could actually just take the final graphical structures, those nice revolving maps, and try to define a metric that then comes to give you some kind of population level of those final graphical structures. I think they're the kind of things that would be interesting to explore and interesting to comment on what you think might happen. So moving on to the SODA or Nottingham analysis, I thought this was a really nice idea because they went back to basics. They said, look, if I'm doing fMRI, there's a whole bunch of pre-processing that people do, and what does it all mean? And to be totally honest, if you ask people who do it, they won't know. It's default buttons on a software. You press it, it runs it through, and then you do your final next analysis, which is the bit that's interesting. Pre-processing isn't interesting per se, except it's incredibly important because, as you say, you do different pre-processing, you get different results. And in some sense, that highlighted one of the aims of the challenge. How does the sort of basic underlying methods that you use affect the results? So I thought it was very nice that they looked at how different smoothing of full-width half maxes affected network connectivity. They looked at using ICA and what happened with different levels of smoothing and see how that affected the ICA. And then what I think the smoothing is one of the most heuristic parts of pre-processing. All the others, you can kind of see what the kind of underlying statistical model is. For smoothing, they stick a Gaussian kernel on, and you move it around, and you pick the full-width half max like that. Now, there are other ways of doing it, and it might be interesting, as I'll talk about later on, to try and compare those. But in some sense, they picked the one that I would have chosen. They'd have picked the one that I said, you know, this is the one where people really have a sort of heuristic way of doing it. So what did they get for their results? Well, I like their graphs. I agree with the question that it would be kind of nice if there was a sort of more formal metric to compare them. But in the end, the idea is kind of nice. You get these things where you get pretty good straight lines for 3 millimeter differences, 3 to 3 and 3 to 6, and the same from 6 to 9 and 9 to 12. But then you get slightly bigger correlation differences between 0 and 12, so 12 millimeter differences in the smoothing, which is kind of what you'd expect. You'd expect if you give a big amount of smoothing to the data, you should get different, at least some kind of differences in the networks than you would if you just don't do any smoothing at all. Well, in some sense, the results were slightly surprising at first in the fact that I would have at least sort of expected to see some differences as you increase the smoothing, because in some sense, you're sort of smoothing your areas. If you think about what your voxels represent, every time you smooth a bit more, you would expect the voxels to sort of kind of contain more information, so you'd probably expect the networks to change a little bit. You couldn't have quite such diverse networks, but maybe 3 millimeters is about the level that you can't really distinguish between, particularly given the intrinsic resolution of the scanner, which is probably somewhere around 6 millimeters. However, it was nice to see that when you do a big one, you do get a difference. So that's sort of one of the nice things to be able to maybe find out is at what point in that sort of continuum does it really start to make a difference. The other interesting and maybe worrying result for everybody who uses ICA is that it does seem to affect the number of ICs chosen. And if you're going to rely on these ICs to mean something, then it would be kind of nice if they were moderately stable. What would be something which would be interesting is to see whether the actual spatial maps of the ICs change, and whether, in actual fact, you're just combining spatial maps, or whether they really are truly completely different ICs that you're getting out, or whether you're having some similarities between the ICs that you see. I'd actually kind of like to know what the spatial extent of the networks are. So does the smoothing actually change what the networks look like, and in actual fact, how much in the brain anatomy do they change? Because in some sense, if the networks don't change very much, because in actual fact you've already got large blobs, large spatial extent on your networks before you start, then when maybe the smoothing isn't going to make a big difference in that case. And again, as I said before, the population level element of this is kind of very interesting. How do you determine the group structure for the different comparisons? Do you want to do individual smoothing, or do you want to do smoothing on a group level? Do you want to use, if you're going to do network analysis across populations, do you really need that smoothing to be the same for every individual, or do you really want it to be different between individuals so that you can kind of capture individual variability before you get to the network analysis stage? And one of the last things is that there are a few methods that don't sort of heuristically choose the smoothing level. There's the sort of scale space analysis methods. There's the wavelet adaptive smoothing method. And maybe it would be interesting to see if you applied exactly the same things, but with those kind of pre-processing approaches, whether you get different networks again, and whether you can use that to see whether that might give you a way of being a bit more formal in how you choose the kind of scale space analysis, kind of scale that you do your smoothing at. So in summary, I think you'll all have to agree that we had 2 really impressive analyses of the data, particularly given that this data was just sort of thrown at them for 6 weeks, and they sort of had very little background except, here, get on with it. I think both of them really took into account the fact that what the data had, and then some of the interesting statistical issues, that you can't just ignore things like correlation. You can't just ignore things about how data is related. And I think that they both have the potential to improve current practice, because people can actually look and say, well, look, if I take these into account, I'll get more sensible statistical analyses. So I'd like to thank both the teams very much for their submissions, and hope that many people here will submit things to the competition next year. Thanks a lot.